Our perception of reality has long been shaped by the human body. We measure the world in units derived from ourselves: feet, meters, centimeters, proportions born of our biology. For centuries, that seemed perfectly logical. After all, why measure the universe by anything other than what we can physically touch? But modern physics has shown us that our scale is little more than an evolutionary quirk. It tells us almost nothing about the universe's deeper structure. So what happens when we try to understand reality beyond ourselves? Enter one of science's giants, Max Planck, a foundational figure in the quantum revolution. Planck proposed a system of units not based on human dimensions, but on universal constants, constants that would remain meaningful even to an alien civilization devoid of arms, legs, or any human form, perhaps made of matter we cannot yet imagine. At the heart lie three fundamental constants: the speed of light, Newton's gravitational constant, and Planck's own constant. Three pillars, three hidden codes of the cosmos. The speed of light is not just extreme, it is absolute. Nothing with mass can ever reach it. Gravity, as measured by Newton and deepened by Einstein, tells us how matter shapes the fabric of space-time. And Planck's constant, that is the heart of quantum mystery. It defines a limit to what we can know. We cannot simultaneously know a particle's position and momentum with perfect precision. It is as if nature drew a veil over reality. Combine those three constants and you derive a unit of length, the Planck length, a number so minuscule it defies comprehension, 10 to the power of minus 35 meters, smaller than anything we can possibly imagine. Yet within that abyss of minuteness lies something profound. In the 1970s, the physicist Jacob Bekenstein showed that a black hole's entropy, its measure of internal information, is proportional not to its volume, but to the area of its event horizon measured in square Planck lengths. In other words, it's not volume that matters, but surface. It is as if the universe told us that information, the essence of what is etched on a cosmic skin, a boundary akin to the pixels of a screen. And here emerges a startling notion. When we try to probe deeper than that length, we must use ever higher energy light. But the more energy we use, the more we warp space itself. At a certain point, trying to observe the infinitesimal creates a black hole, and then we see nothing. Reality defends itself by hiding its core. There is a horizon, a true limit to what we can know. This limit, the Planck length, may indeed be a pixel of the universe, a fundamental brick, the deepest level of zoom, the grain of space itself. Physicists often speak of nature as encoded in mathematics, but what if the very structure of space itself is digital, quantized into these Planck-sized units? It forces us to ask, is the universe continuous, like flowing water, or granular, like a mosaic? If the latter, then the Planck length isn't just a number, it's the smallest meaningful distance. Beyond it, concepts like here and there might no longer apply in any classical sense. But even this could change. Some theories, such as those exploring extra dimensions in the cosmos, suggest this number might shift. Experiments at the Large Hadron Collider are searching for evidence that hidden dimensions could strengthen gravity at certain scales, altering the size of that minimal unit. For now, the Planck length stands as the boundary, a figure derived with mathematical precision, yet wrapped in mystery. It tells us that reality has texture, a pattern beneath the surface of all that exists. That pattern, that minimal unit of existence, is perhaps the closest we have come to unraveling the source code of the universe. These questions don't only challenge the physicist, they touch something ancient within us. Civilizations have long sought the first principles of existence, from sacred geometry to philosophical atoms. Now, with modern physics, we peer into that mystery with sharper tools. The Planck length may not only represent a physical limit, but echo a deeper truth, that nature itself is structured, discrete, and perhaps even intentional. Deep within the dying hearts of stars lie truths that stretch the bounds of human understanding. When a star exhausts its nuclear fuel, fusion, the force that once held it up, flickers out. Gravity, that ever-faithful pull, begins collapsing the stellar core inward, and in that moment, a silent dance begins between two titanic frameworks of reality, quantum mechanics and gravity. What halts this collapse is not a wall or structure, but something far stranger. It's a law that emerges from the quantum fog, the uncertainty principle, formulated by Werner Heisenberg. In the quantum realm, the more precisely we try to know the position of a particle, the more uncertain its momentum becomes. Confining an electron makes it resist, jitter, and press outward, as if the universe itself rebels against being boxed in without consequence. But this resistance is not alone. Another quantum guardian enters the stage, the Pauli exclusion principle, born from the mind of Wolfgang Pauli. It declares that no two electrons can share the same quantum state. As collapsing matter pushes electrons closer together, their refusal to overlap generates a pressure so potent it can hold up an entire star. This, then, is a white dwarf, a stellar corpse held aloft by the sheer unwillingness of its particles to be crammed together. This cosmic interplay between quantum laws and gravitational collapse not only shapes the fate of stars, but invites a deeper contemplation of the laws that govern all matter. Imagine this. The atoms that make up your body obey these same rules. The resistance of electrons, the jittering uncertainty, the unwillingness to be confined. These are not just phenomena of the distant stars, but the very foundations of your own existence. In this sense, the death of a star is not remote. It's a mirror held up to the laws that animate everything, from the cells in your hand to the galaxies above. Yet even this defiance has a boundary. In one of physics' most elegant revelations, Subrahmanyan Chandrasekhar calculated the upper mass limit for such stars. Should a star's mass exceed roughly 1.5 times that of our Sun, quantum pressure alone cannot save it. The collapse continues towards neutron stars, or perhaps the dark abyss of a black hole. What's astonishing is that this limit, the Chandrasekhar limit, emerges from just 3 constants: Planck's constant, the speed of light, and Newton's gravitational constant. The very same trio that define the smallest conceivable scale in the universe also delineate the grand thresholds of cosmic collapse. It's a breathtaking symmetry. The same code that underlies the flicker of particles at the quantum level also scripts the fate of stars across the heavens. From the Planck length to supernova remnants, the architecture of the cosmos is written in invisible ink. Yet its grammar is exact, its logic profound. This convergence of the micro and the massive reveals something extraordinary, that from a handful of constants, humanity can unlock the behavior of celestial giants. The Planck scale, though utterly unreachable in daily life, echoes through the dying embers of the night sky. In these fading stellar cores, it is not only light that extinguishes, it is also the boundary of knowledge that glows anew. Here, between collapse and resistance, the cosmos unveils its most sacred rhythm, the point at which science fractures and is reborn. The Planck length, this minuscule boundary of the universe, is so staggeringly small that it completely escapes the human imagination. To grasp its insignificance, consider this. If a proton, already unimaginably tiny, were expanded to the size of our solar system, then something the size of the Planck length would be equivalent to a single living cell. That ratio stretching from the quantum to the visible is so extreme that our minds dissolve in the attempt to visualize it. It's as though we've hit the boundary of what our evolutionary minds were ever designed to comprehend, an invisible wall where numbers become abstractions and intuition fails. Yet our struggle with scale does not end there. As human beings, we are naturally attuned to our own size. We grasp what is familiar, centimeters, meters, perhaps a few dozen meters. Distances of several kilometers, maybe even hundreds, are manageable. We've walked them, driven them, flown over them. A train journey or a transatlantic flight can be imagined with ease. But beyond that, the scale becomes mist. It becomes myth. Our brains evolved to throw spears and tend crops, not to measure the yawning gulfs between galaxies. Yet here we are, daring to grasp the ungraspable. Even for those who have left the Earth like Buzz Aldrin, the distance between our planet and the Moon, some 400,000 kilometers, represents a tangible triumph. But what happens when we venture further? The Sun, for example, sits at roughly 150 million kilometers from Earth. How does one give form to that number? We see it in the sky every day, its disk appearing no larger than the Moon's, an elegant coincidence of celestial geometry. But that same Sun could contain over 1 million Earths. Its diameter is about 100 times greater than our planet's. If you attempted to fly around it in a commercial airliner, the journey would take almost an entire year. And yet, the Sun is an ordinary star. Let us consider Voyager 1, the most distant object ever launched by humanity. It now travels more than 150 times the distance between the Earth and the Sun. Light itself, traveling at nearly 300,000 kilometers per second, takes more than 22 hours to reach it. That's merely the threshold of the outer solar system. Include the Oort cloud, a vast icy shell of comets and fragments, and our solar system stretches perhaps a full light year in radius. The nearest stellar system, Alpha Centauri, lies about 4 light years away. That means light, the fastest thing in existence, would take 4 entire years to reach it. Truly inconceivable. Our galaxy, the Milky Way, holds between 200 and 400 billion stars. Its diameter is about 100,000 light years. That means light must travel 1,000 years for every 100th of that distance, across a single cosmic city of stars. Then there is Andromeda, our neighboring galaxy, 2.5 million light years away. When you gaze at it under a dark sky, know this: the light entering your eyes began its journey before human beings ever walked the Earth. It has traveled for millions of years, across a universe that is constantly expanding. And even that is not the end. With tools like the James Webb Space Telescope, we've detected galaxies whose light has been traveling for more than 13 billion years to reach us. Beyond them, we find the cosmic microwave background, light born just 380,000 years after the Big Bang. And where is that light from the dawn of time now? Thanks to the expansion of the universe, the place from which it was emitted now lies over 46 billion light years away. And still, beyond that, there is more. We know, through mathematics, through observation, that the universe continues beyond what we can see. Perhaps it is infinite. Probably it is. Infinity, a word we can say, but cannot truly fathom. It sits at the edge of reason, where imagination peers over the cliff of the unknown. So even something as basic as a single light year, a unit astronomers use casually, is already beyond real human comprehension. The universe is not merely vast, it is fundamentally inconceivable. And within this abyss of scales, from the infinitesimal to the incomprehensibly large, our existence stands as a miracle of perception, a flash of awareness inside a structure too immense to grasp. A star is at its core a battle. Gravity tries relentlessly to crush it, to silence its brilliant blaze. But the counterforce, nuclear fusion, pushes back from within, keeping the star alive. For over 4 billion years, this delicate balance has sustained our sun. This harmonious tug of war is not just a marvel of stability. It's the mechanism that powers life itself. Without this sustained equilibrium, no warmth would reach our Earth, no energy would drive our atmosphere or oceans. It is quite literally the beating heart of the solar system. Yet no star burns forever. When its nuclear fuel is exhausted, its core loses the energy needed to resist gravity. At that moment, the question arises, does the star collapse infinitely? Or is there a deeper law that intervenes? One of the most elegant ideas in modern physics offers an answer. In the 1930s, Subrahmanyan Chandrasekhar demonstrated that even when nuclear reactions stop, matter still has one last defense: its electrons. Under immense pressure, these electrons resist compression, not through brute force, but through the subtle laws of quantum mechanics. The first of these laws was formulated by Werner Heisenberg, the uncertainty principle. The more tightly we try to confine an electron, the more uncertain and energetic its momentum becomes. This uncertainty manifests as a kind of quantum agitation, a jiggle that builds pressure. Think of it as a quantum spring coiling tighter and tighter until the pressure becomes palpable, even in the vast silence of space. This invisible internal motion is no less real than the pull of gravity itself. Add to this the Pauli exclusion principle, proposed by Wolfgang Pauli. It states that no two electrons can occupy the same quantum state. So under compression, electrons spread out, repel, and continue to jiggle. This invisible motion exerts real pressure, strong enough to support the dying core of a star. But even this quantum dance has limits. If the star is too massive, the electron's quantum agitation approaches the speed of light. At that point, they can resist no more. The star collapses beyond the quantum boundary, possibly into a neutron star or even a black hole. In such cases, the collapse becomes unstoppable, leading to some of the most extreme and mysterious objects in the cosmos. Regions where not even light can escape, and where the laws of physics as we know them break down. However, if the star's mass remains within a certain threshold, it can stabilize as a white dwarf, supported entirely by the quantum pressure of its electrons. Chandrasekhar calculated this limit precisely, approximately 1.4 times the mass of our Sun. It's a profoundly significant result. Not only does it predict the fate of stars, but it also connects celestial mechanics with the fundamental constants of the universe. How did physics arrive at this threshold? By using the same constants that define the Planck length, Planck's constant, the speed of light, and Newton's gravitational constant. When combined with the proton mass, they yield a new scale, the Planck mass, which, surprisingly, is around the mass of a speck of dust. From that foundation, one can derive gracefully the Chandrasekhar limit. This perhaps is the most beautiful expression of theoretical physics. Abstract ideas, born of human thought, revealing visible truths in the sky. A star caught in the tension between collapse and resistance, between gravity and quantum rules, shows us that the cosmos can be described with just a few words, yet each word carries the weight of universal wisdom. We are witnessing the dawn of a new era. For the first time in history, humanity stands at the threshold of becoming a multi-planetary civilization. For decades, space exploration remained the exclusive realm of national governments. But today, a quiet technological revolution is flinging open that frontier. The development of reusable rockets, pioneered by companies like SpaceX and Blue Origin, has drastically reduced the cost of accessing space. This shift has triggered a steady industrialization of low Earth orbit, just a few hundred kilometers above our heads. And it's no longer only about placing satellites for weather forecasting or communications. We are now seeing the construction of platforms for scientific research, space tourism, and even manufacturing in microgravity conditions. Constellations of satellites, like Starlink, are already transforming global connectivity. In the coming years, hundreds, perhaps even thousands of new systems will orbit our planet. This rapid expansion brings an urgent question. How do we organize traffic in space? There is still no comprehensive international framework to regulate satellite proximity or prevent collisions. Some have proposed an air traffic control-like model, with shared protocols for avoidance and coordination. While these discussions may sound technical, they conceal a deeper message. As the great Carl Sagan once said, we are only just beginning to wade into the cosmic ocean. And, as he added with awe, the water seems inviting. Beyond Earth's orbit, the opportunities become even more extraordinary. On the International Space Station, researchers have already carried out promising experiments. New methods for cultivating cells, growing purer crystals, and developing advanced semiconductor technologies. Microgravity, so alien to us on Earth, presents unexpected advantages for science and industry alike. But the real leap lies further ahead. With the right infrastructure, we could begin to reach near-Earth asteroids rich in rare metals and materials. This would completely redefine our relationship with natural resources. Many of humanity's historical conflicts have stemmed from scarcity and the struggle to control limited supplies. In space, raw materials are virtually infinite. We would no longer be forced to exploit a planet already strained by our presence. Imagine a future where cities rise not only on Earth, but also on the Moon and Mars. A future where human expansion no longer relies on environmental destruction. That possibility is now closer than ever. This shift isn't merely technological. It signals a profound philosophical awakening. Humanity is no longer confined to one world. It is becoming, in the truest sense, a species that spans worlds. This expansion compels us to consider not just where we go, but how we go, and what kind of legacy we leave behind. It challenges our concepts of sovereignty, ethics, and environmental stewardship on a cosmic scale. Each satellite we launch, each habitat we build, becomes a statement about our values. We must ask ourselves, will we replicate old habits, pollution, inequality, or will we pioneer a new form of civilization, one founded on collaboration, sustainability, and respect for both known and unknown ecosystems? This cosmic transition urges us to act with foresight, unity, and a deep sense of purpose. And yet, every step forward comes with responsibility. Managing space is not only a technical challenge, it is a moral and global one. Just as we must regulate artificial intelligence and quantum computing, the colonization of space demands that we act as a unified species, because in the end, we all inhabit the same vessel, Earth, a pale blue dot drifting silently through the vast darkness, circling the sun in quiet revolution. What we choose today as a civilization will shape the course of our voyage into the cosmic ocean. It is entirely natural to feel insignificant when faced with the immensity of the universe. How could we not? Each of us is merely a collection of atoms inhabiting a speck of dust, orbiting an ordinary star among 400 billion others, all within our own Milky Way galaxy. And when we remember that there are over 2 trillion galaxies in the observable universe, the sense of smallness becomes overwhelming. From a purely physical perspective, yes, we are inconsequential. But what if value resides not in size or mass, but in something far more subtle, something deeper? For many years, I have maintained that, despite our tiny stature, we could be astonishingly valuable. If intelligent civilizations are indeed rare, as some suggest, perhaps fewer than one per galaxy, then humanity may be a precious anomaly. We might truly be the only place in the Milky Way where matter has awakened to consciousness, where atoms arranged in a unique way can think, love, probe the universe, and reflect on their place within it. Carl Sagan, with his trademark eloquence, reminded us that we bear a responsibility to the cosmos, not out of arrogance, but perhaps because we may be the universe's sole conscious voice. A voice that, if silenced, might never resound again for billions of years, if ever. We are the cumulative result of 13.8 billion years of cosmic evolution. An unbroken chain of events has led to our existence, yet that continuity is far from guaranteed. Life on Earth is fragile, and our civilization even more so. Each moment of conscious awareness is, in its own right, a cosmic rarity. Sometimes new insights force us to shift our perspective. I recently re-encountered a compelling argument from David Deutsch, a pioneer of quantum computing. In his work, he revisits a profound concept originally introduced in the anthropic cosmological principle by John Barrow and Frank Tipler, a text that significantly influenced me during my university years. The central notion is provocative. We should not assume that life will remain merely a local curiosity without broader significance. For life, particularly intelligent life, has transformative power. Consider Earth itself. Its oxygen-rich atmosphere did not exist at the planet's birth. Life, through photosynthesis, created it. And our civilization has already left visible traces from space. The lights of cities, the vast alterations to landscapes. These speak to consciousness's ability to reshape entire planets. If such change is possible in a single generation, what might we achieve in a millennium or a million years? Perhaps even over a billion. There is nothing in the laws of physics to prevent a civilization from persisting, evolving, and expanding. And if that happens, its capacity for impact could extend far beyond a single planet or star system. And so, the question arises, what if we are just at the very beginning of a journey that could redefine not only ourselves, but the very nature of existence itself? Imagine a future in which knowledge accumulates at an exponential rate, where civilizations harness not only the energy of stars, but the intricate structures of space-time itself. With deeper understanding might come the ability to manipulate gravity, engineer entire environments, or even navigate dimensions currently beyond our reach. If that path is real, even hypothetically, then life might not only be a brief flicker of awareness in a silent cosmos. It could become the architect of meaning, the mechanism through which the universe understands itself. Perhaps, in the farthest future imaginable, life is not the observer of the universe, but its active participant, co-creator, and guardian. This perspective does not erase our insignificance, but reframes it. We may not be physically vast, but we are potentially meaningful, because a cosmos devoid of consciousness might be expansive, but eternally silent. What if life, the spark we observe today only on Earth, were not a mere passenger in the universe, but its future architect? This idea may sound like science fiction, but it emerges from the most rigorous and visionary thinking in contemporary physics. Imagine for a moment that humanity overcomes its current challenges: ecological fragility, conflicts, external threats. Imagine we become a mature spacefaring civilization, capable not only of survival, but of expansion beyond Earth. Could we, over time, begin to mold the very cosmos? This argument is far from preposterous. Look at Earth. The atmosphere we breathe, rich in oxygen, is a direct product of life. Without photosynthetic organisms, our planet would be unrecognizable. Our civilization, with cities, infrastructure, and nighttime illumination, has already sculpted the surface of Earth. If life has altered an entire planet, why not consider that it might do so on a much larger scale? As our technology advances, it becomes conceivable that we might undertake projects such as terraforming Mars, colonizing the moons of Jupiter or Saturn, and eventually engineering entire solar systems. It's not beyond the laws of physics to intervene even in stellar processes or manipulate the course of stars. And if we extrapolate this capability over millions or even billions of years, an astonishing prospect unfolds. A civilization advanced enough to influence the evolution of entire galaxies. It was David Deutsch who recently revived this idea, though its roots stretch back to a seminal text, The Anthropic Cosmological Principle, penned by John Barrow and Frank Tipler. This speculative work envisions life not merely surviving, but becoming the protagonist of cosmic history. Perhaps its most dramatic proposal is the so-called omega point cosmology. It envisions a universe that, rather than expanding forever, eventually collapses in the distant future. In that moment, a sufficiently advanced civilization could intervene, manipulating matter and energy to slow the collapse while increasing its capacity to process information indefinitely. The outcome: a universe where life, far from being a footnote, is the ultimate engine driving evolution. In this scenario, time is not measured in ordinary units, but by the volume of information processed. If that capacity diverges towards infinity, we're speaking, in essence, of a form of cosmic immortality. It is crucial to emphasize that this idea is not a prediction. It is speculation in its most refined form. But even as a mental exercise, it holds immense value. It challenges the assumption that life is marginal and invites us to imagine a future where thought, consciousness, and intelligence not only endure, but shape the destiny of the universe. Indeed, if we accept that life has already reshaped a planet and imagine its progression over millions of years, then what would prevent it from assuming the role of a universal sculptor? Picture a galaxy where countless worlds, once cold and inert, are awakened by conscious intent. Planets terraformed, stars stabilized, even black holes harnessed as sources of power or knowledge. In this far-flung epoch, intelligence might no longer be confined to biology. Artificial minds could exceed the limitations of organic matter, persisting across epochs and surviving cosmic cataclysms. Their thoughts, stretching across vast interstellar networks, might resemble the neural patterns of a cosmic mind. The universe, once indifferent and chaotic, could then evolve into a tapestry woven by sentient design. Perhaps our current technological dreams, quantum computing, artificial general intelligence, interstellar propulsion, are mere whispers of that destiny. In contemplating such futures, we do not only stretch the boundaries of science, we elevate the role of consciousness as the potential author of cosmic order. We do not know if this will come to pass, but the mere fact that it is physically feasible alters the nature of the question entirely. If life endures, it may be far more than a fortuitous accident. It could be the creative principle of all future cosmic evolution. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.